last lecture we started discussing about the stability of a system in terms of its potential energy profile. So, what we said that a third way of looking at the system in mechanical equilibrium is that the condition of mechanical equilibrium is that the potential energy of the system is at an extremum, which means either minimum or maximum. Let us understand this concept by taking an example. So, this when we sort of do this energy diagram method, so we are sort of we are, for simplicity, we are going to ignore all the friction present in the system, because it is slightly conceptually difficult to define a potential energy in presence of friction, because friction is not a force that you can express as a derivative of a energy function. So, here is an example. So, we have a mechanism as shown in this figure. A 10 kg block is attached to the rim. So, this is a 10 kg block attached to the rim of a disc. So, this is a disc whose radius is b, which is equal to 300 millimeter, and at the center there is this block is also attached to some wheel which can rotate, and this wheel is attached to a spring BC. Now, this is the mechanism. So, if you rotate, if you move this block along the rim, then if you so let us say at the vertical position is where the spring is unstretched. So, if you move the block in this direction, then because it is attached to the way this mechanism is designed, then the spring is going to stretch, and if you move the block from this direction, then the spring is going to compress, and the block, if the block moves this way. Equivalently, if you compress the spring, if the spring compresses, then the block moves in the left direction, and if the spring stretches, then the block moves in the right direction. This is the mechanism. So, the question is, determine the equilibrium positions and state whether the equilibrium is stable, unstable or neutral. So, the first question is, how do we determine the position? So, in this case, so what is our system? Our system is the block with the mass 10 kg. So, how do we determine its position? It is clear in this, from this figure, that it has a single degrees of freedom, even though it rotates on a disc which is a 2D object, but it is constrained to move along. So, the constraint is such that the distance from the center of this point O to the block is always fixed. So, it is a single degrees of freedom system. So, we can represent this angle theta, so as a very independent variable. So, each value of theta represents one position or one configuration of our block, and in the given in the problem it is given that when the theta, so this angle is theta, it is measured from this vertical direction. So, this vertical direction represents the theta equal to 0 configuration position. So, I hope now you have some idea about the mechanism. So, let us now go to analyze the problem. So, what we are trying to our approach is the energy diagram approach. So, we are going to construct an energy diagram which I have shown in this picture here. So, this is the energy profile U is the total potential energy, and this is our angle theta. So, we are going to write down, our goal is to determine this shape of this profile. So, for that, what are the potential energy, what are the forces? So, instead of force, if you think in terms of energy, you can easily see that this block. So, let us say if I take this block plus this spring. So, let us say our system is block plus spring. In fact, in this case, to properly define this potential energy, we have to include the earth also in our system. So, this is our system, so that there is no external force acting on this system. Now, there are two contribution to the energy. The first contribution is, as you change theta, the position of the block changes, which means the gravitational potential energy of the block changes. So, how much is the gravitational potential energy? Let us take this point O as our origin, and this is our x axis, and let us say this is our y axis. So, theta equal to 0 is the y axis. Then, and if I measure, if I take the 0 of the reference level of the gravitational potential at x axis, then its gravitational potential energy is given by the height of this block from the x axis, and from this picture it is clear that this height is actually, so this angle is theta, so height is b cos theta. So, that means the gravitational potential energy is mg times h, which is mg b cos theta. So, if h is positive, it is positive, if h is negative, it is negative. The second one is that as the block changes position, the spring can stretch or compress. So, that gives you another source of potential energy. So, the spring potential energy now, how much is the stretch of the spring? Suppose I start the block from a theta equal to 0 position and I move it to a position where it is at the currently. So, then it is clear from this picture that the point which was here on this small dial, the green, then the stretch of the spring is given by this particular arc length, which makes the same angle theta. So, this is the stretching. So, let us say it goes to the right. So, it is a stretching of the spring. So, the stretching of the spring is given by this particular arc length that I have highlighted here, which is the radius of the smaller dial, which is a, times the same angle theta. So, this is from the mechanism. So, note that if theta is negative, so that means the block moves on the left, then this actually is a compression. So, I am assuming that you are familiar with spring potential energy. So, the spring potential energy will be given by half times the spring constant k times the stretching, which is, then for our system of this block and spring and earth, the total potential energy of this particular system is given by the two particular contribution. You can have to add them. So, let us now you see that there is only one variable on the right hand side, and hence this is a profile of potential energy, and you can actually, it is a profile with a single independent variable theta, and you can draw them. And what I have shown on this picture here is nothing but this particular function. So, how do you guess what is the value of this function? What is the shape of this function? Well, it is easy to guess. Note that it has two terms. So, the trick is to draw each term. So, you know that how cos theta look like. All these things are constant. So, let us be it will be easier if you sort of plug in the numerical values. So, let us calculate the value of mg times b. So, m is given to be 10 kg let us assume G is 9.81 and B is the radius. So, remember that we should express this radius. This is very important for numerical calculation, that to be consistent always use, try to use SI unit. So, you is given in the millimeter, convert it into meter. So, that is 300 millimeter, which is so, and I also highlight deliberately these units. So, what is going to should be the unit of this quantity mgb. So, mgb has, you expect it has a dimension of energy. So, you expect that it should be, the unit should be joule in SI, and you can verify that if you make this product, the unit is indeed joule. And if you sort of look at the numbers, so this will cancel with this power. So, we get 9.81 into 3, which is about 29.43, and this is kg meter square per second square, which is joule. Then this k a square k is 4 kilonewton, kilo is 10 to the 3 Newton per meter, times a square, which is 80 into 10 to the minus 3 whole square meter square. So, again you see that the unit is Newton times meter. So, 1 m gets 1 meter gets cancelled. So, it is Newton times meter, which is again joule. Now, the numerical value. So, what we have is half into 4 into 80 into 80. So, there is a 10 to the power minus 6 coming from the square and 10 to the power plus 3. So, you have a 10 to the power minus 3, and you have a, if you simplify it, you will get something like 25.6 joule. So, this is 8 into 8 into 4 by 2, which is half into, which is 12.8 joule. So, then this u theta is equal to 29.43 cos theta plus 12.8 theta square, and the unit is expressed understood to be joule. So, how do this function looks like? So, the way to do it is to sort of first plot each of them. So, you see that you know how the cos theta looks like. So, it varies from plus 1 to minus 1. So, that means some constant times cos theta will vary from plus a to minus a. So, the cos theta will give you, so at theta equal to 0, cos theta is 1. So, it has the maximum. So, it looks like this. On the negative side looks like this. Now, this something a theta square, you know that this is an equation of parabola. At theta equal to 0, this is 0, at theta equal to and then it grows. So, then the total, if you add them, so at theta equal to 0, it should start from here. If you add the two pieces, two terms, this is the term second term and this is the first term. So, the net force, net profile is going to be something like, now when start from here and it goes there, and then it makes a turn, because for small value of theta this cos theta term dominates, this second term contributes little, but as you increase theta larger and larger, then the cos theta can never become bigger than 29.43, but this second term does not have any restriction. So, for large theta this is going to be the dominating term, the spring term is going to be the dominating term. So, we expect a net profile to look like this, and indeed if you draw this function you actually see that. So, now we coming back to the question. So, we have to determine the equilibrium positions. Now this is easy. Once you draw this profile, this is easy. You see from this profile or even to look at shape of this curve that there should be 3 equilibrium position, because there are 2 minima of u, and 1 maxima. So, there are 3 different values of theta where the slope of u, the du d theta is 0. Three solutions. Now, does it make sense? This is what mathematics gives you the answer, but does it make sense physically? Well, so the first solution is theta equal to 0, we see a solution. So, at theta equal to 0, the spring is unstretched and this is sort of at the top position. So, you can see that spring is unstretched means there is no contribution from the spring, but this block is here and this is sort of an unstable position, but it is kind of at equilibrium. Now, what happens if you sort of the blocks gets disturbed slightly? Now, it sort of starts to fall along the rim. Let us say it falls on the right hand side. Now, as it falls, the spring starts to sort of stretch, and because of the stretching of the spring will try to compress, so that it will naturally its tendency is to compress downwards, which means it is trying to give a force on the give a force on the block on the opposite direction. So, it is trying to prevent the fall of the block. So, then there will be some position at some finite value of theta, there will be some position where you expect that these two effects will balance each other, and that will be a equilibrium position. Similarly, on the other side, if it starts to fall on the left hand side, then the spring is going to compress and the spring will not like it. So, it will try to stretch itself. So, again the net effect is to give try to prevent the fall of the block. So, again when this force will initially the spring force will be small, and as the angle theta increases, then it becomes more and more stronger. So, eventually it will balance this fall and it will stop the fall of the block. So, hence you will get another position. So, this is this left hand side position for negative theta, and the other one is the this right hand side position for positive theta. Now, formally, since we have u is some mgb, let us write it in general terms, half k square theta square. Then if I calculate the du d theta, then we get minus mgb sin theta plus k a square theta, and if we set it to 0, so that is the condition for extremum, maximum or minimum, then we get an equation that sin theta is equal to k a square divided by mgb times theta. So, this is an equation. Now, this equation is a non-trivial equation in the sense that it is we have to solve it numerically. There are computational algorithms by which you can solve this kind of equation. It is a nonlinear equation, or graphically. What do we mean by graphically? So, you take this theta. So, there are consider this as some function 1 of theta, and this is a second function 2 of theta. So, the second function is like y equal to mx. So, something constant times theta is and y equal to mx. Let us say this is this function k a square theta by mgb, and the sin theta, you know that sin theta starts from 0, and this is sin theta. So, you can see that there are 3 points of intersection so these points of intersection represents the fact that the values of sin theta is equal to the value of this function. So, this is sin theta. So, these are the points which satisfies values of theta which satisfies this particular equation, and you can see from this graph that there are only 3 solutions possible. Now, if you want to know the whether this is stable or unstable, and it is clear from this graph or from looking at this equation that theta equal to 0 is a solution, and the other 2 solutions are some particular values of theta naught, and by symmetry you can see if theta naught is a solution, then minus theta naught is also a solution. So, they must be symmetric. Now, let us calculate the second derivative. So, the second derivative from this equation is minus mg b cos theta plus k a square. Now, from the given, if I plug in the values, so we get 29.43 cos theta plus 12.8. So, if I take, so this is minus. So, if I take the theta equal to 0, we can check, it is easy to check for theta equal to 0 that this is negative, which means this is an unstable solution. So, sorry, unstable solution, which means that unstable equilibrium. Okay. So, I hope that this gives you some idea about how to approach this kind of problem, to do this kind of problem. So, here I want to mention quickly about some interesting application of this concept. Remember that in the last lecture we said that the energy diagram method of doing stability analysis, which is useful to sort of understand the question, what happens if you move away from the stable point and how many equilibrium configurations are possible. But there are various interesting examples beyond mechanics. For example, let us start with something in the mechanics. So, we can use this energy diagram is a very powerful method. We can use this to determine pictorially the bound states and unbound states of a system. So, an famous example is the two body system, for example, motion of earth around the sun or motion of an electron around the nucleus in a hydrogen atom, etc. So, let us say that r, which represents the distance between two objects, and the configuration of our system, which consists of two point particles, are specified completely by uniquely by r. And then we have this, for each r there is some potential, system has some potential energy, and this red line, the blue line represents this potential energy profile as a function of different positions r. Now, the system is moving, so it also has a kinetic energy in general. So, the total energy of the system is given by the kinetic energy plus the potential energy. So, these green lines are the total potential energy of the system. Now, we have shown you 3 different values of the total energy of the system. Now, if you do the analysis further, turns out that if you just look at this total energy, you see that this is cutting the this potential energy diagram profile at 2 points, and this means, and we are, so these are in a system where there is no friction, so the total energy is constant. So, it immediately tells you that the distance separate this r, values of r can only vary within this range. So, the distance between the two objects cannot be less than this particular value and cannot be bigger than this particular value, and the system is stable. This kind of state is called a bound state. Now, if I go to the slightly increase the total energy of the system, then we see that the range of values of the over which the separation the R can take the possible values of allowed values of R has increased, but still bound between a maximum and the minimum. Now, contrast this with the situation when the total energy is at the level C. In this case, you see that it is the R has a minimum distance, so it cannot go beyond this distance, but on the other side there is no restriction on the highest value possible for R, the separation. It can be any separation is possible. So, this kind of state is a unbound state. So, just by making this potential energy diagram, we can, it is very easy to understand the nature of the motion of your system in a qualitative way. For example, this means that the if you consider the earth and sun system, it is basically means that the sun is the motion of earth is bound to move around the sun. Its distance between the sun and earth varies, but it varies within a range, it cannot be anything. Whereas, this C position can, for example, perhaps represents the motion of a comet. So, it also moves around the sun, but it distance, so it can have a closest this approach to sun, but there is no limit on the furthest approach. So, the motion of the comet around the sun is not bound. The another example is from chemistry, where the chemical reaction is, so the how the chemical reaction happens, the mechanism of chemical reaction. So, there it is sort of thought of understood as a transition from a state, one state to another. So, the initial state is the state of the energy state of the reactant components, and the final state is that of the product. And here, so the initially this was reactants were not kind of stable, so they are not doing anything, and then when they come in contact with each other, or you sort of mix them together, then they do the chemical reaction and they go to a second state. So, this kind of describing this kind of chemical reaction, this potential energy diagram is a very easy way to sort of see how the reaction is moving from start to finish. The third example is that the things become really interesting when, so far in our examples, the system configuration or state or position is completely specified by 1 degree of freedom, single degrees of freedom. But things become really interesting when your number of independent variables becomes more than 1. So, in this case, the potential energy is a function of more than 1 independent variables, and so hence it is called a energy surface, or if the number of variables is 2 and if the number of variables is 3, then it is called an energy landscape. So, it is not important to know what are the details of this picture, but this is showing a 2 independent variables, one plotted on the x axis, one plotted on the y axis, and these different colors represents the values of energy. So, the gray has the highest value of energy and blue has the lowest value of energy, and these lines are sort of contours of equal energy. So, it is sort of kind of a height map of a, as you see. So, the blue is the deepest part of the deepest region, and the so for example, the green is higher, the energy is higher, and the gray the red, the energy is even higher. So, this is like a kind of a cross section. So, if you look at a kind of a well like this kind of shape, then if you sort of do a cross section, then what is the depth of that part. So, this kind of map is also common in, let us say, your atlas in various map in the context of geology. So, where you sort of try to know what is the depth of an ocean floor or the height of a land mountain from the sea level, it is the same thing. And immediately by looking at this curve, you look at what is the region where the energy is minimum. So, the energy is minimum is the position of the most stable configuration. So, you can see just by looking at it, you can easily identify the visually the region with most stable configuration. Now, even more generally nowadays, so some of you will be interested in going to machine learning, so in different problems that involves machine learning or which are kind of called technically called optimization problem. So, we can even generalize from the potential energy to something called a cost function. So, this concept of cost function or fitness function is kind of has the same is kind of can be used is a function that is used to find the optimum state of a system, and this is a very generic function because it is used beyond the physics. So, it is used for example in curve fitting, in various machine learning problems, in economics, in stock market analysis, in biology, in analyzing the evolution theory, the about the proteins, the functions of proteins, drug discovery, etc., etc. So, in usually in those cases, the number of independent variables to define the cost function is usually very high, and hence so the surface instead of a simple 1D function or 2D surface, you have a very complex function. The important point of feature, most important feature that you should remember of this kind of complex function at high dimension is that there is always, no matter what is the details of your system, there is always multiple equilibrium configuration possible, more than one minimum and maximum. So, this is the most important feature of this complex function. So, this is something that is beyond the scope of this mechanics course. I am sure you are going to learn them in different other courses about these things. I just mentioned here, so that because it is essentially the same concept of energy, the kind of generalized version of the potential energy. You have some configuration or state of the system from which you compute a number which you call the cost function, and then you have for so you have a profile of the cost function, and for some values, some configurations are optimum, in the sense the cost function is minimum. So, the potential energy or the cost function is at minimum, and then the problem is about finding those states. So, with this we finish our discussion on mechanical equilibrium. So, in the next lecture we are going to look at a very important force, which is the friction force. Thank you.